to follow up the discussion. Allow me to welcome our facilitator, Teacher Moses. Can you just do a microphone check?
Hello, everyone. I hope you are able to hear me.
Yes, Teacher Moses, you are clear and we are good to start.
So I'm just requesting for about like 2 minutes. See, I set up everything, then we can start our session. So good evening, everyone. I'm Teacher Moses, as the Chakazi was told you. I'm a teacher of physics, and the A level I mainly teach physics paper 1. So today, in today's facilitation, we're going to be discussing some of these questions in this document here, which is already shared to you. So paper 1 is made up of 3 sections. We have section A, where we have mechanics. We have section B, where we have heat and the thermodynamics. Then we have section C, where we have modern physics. We shall be able to discuss some of the items in the mechanics C part, and we shall also look at some other questions in the heat part. Then I think we shall wind up with some other questions from the modern physics part. Because of time, we may not be able to go through all the questions, but I think I'll be sharing with you the solution guide for all the numbers in this document. So for the part of mechanics, I'm going to focus on the first question. Then I also look at the second question. Then we'll be leaving this question 2, question 3, and the question 4. For the interest of time, then we go to section B. I think, are you able to hear me very well? So the first question is asking us to define scalar quantities and the vector quantities. Scalar quantities, basically these are the quantities which have only magnitude and they have no direction, whereas vector quantities, these are quantities that have both magnitude and direction. Then examples of vector quantities and the scalar quantities. Among the examples of scalar quantities, we have distance, we have speed, we have time, we have mass of a body. Then examples of vector quantities, we have velocity, we have displacement, we have acceleration, we have force, we have momentum. All those are examples of vector quantities. Then part B, they are asking us to define what is meant by dimensions of a physical quantity, or what are dimensions of a physical quantity. Dimensions of a physical quantity here, this is the relationship between the fundamental quantities and the derivative quantities. Or someone else can say this refers to the powers to which the fundamental quantities are raised. Powers to which the fundamental quantities are raised to produce derivative quantities. And here we have the fundamental quantities. We have mainly 3 examples of fundamental quantities where we have mass, we have length, and time. Those are the major fundamental quantities that we focus on at this level. So, Roman numeral 2 of section of part B, we have a question. The expression for the velocity v of sound along a load of material of Young's modulus E and the density is given by v squared is equal to E divided by rho, whereby E is standing in for Young's modulus and rho is standing in for density. They want us to show that this formula here is dimensionally consistent. So now for this case, I'm going to share with you an open screen. I'm going to share with you an open screen where I'm going to be doing some calculation and some other parts. So I will share with you this other part. So we have our v squared is equal to E divided by rho, whereby E is Young's modulus and then rho is density. Then V is the velocity of the sound along that medium. Now for this case, we shall begin by saying our Young's modulus E is equal to Young's modulus is given by tensile stress. divided by tensile strain. Now for this case, our E is going to equal to tensile stress is given by force divided by area, which will be divided by tensile strain. This is L divided by extension. So it is very, very important for us to be knowing the formulas of some of these quantities in this expression. Now from here, let us begin with the dimensions on the left-hand side. Dimensions on the left-hand side, we have our V squared. Now for this case, whenever I put square brackets here, we are always trying to show dimensions of that physical quantity. Now we have our V squared on the left-hand side, so we shall have V squared. And for this case here, V is the velocity of the sound wave along that medium. Now, the simplest way for you to be able to master these dimensions here is by looking at the SI units of that given physical quantity. Now, velocity is given in meters per second. Those are the essence for meters per second. And the meters, we are always using L, that is its dimension, capital L. Then time is always capital T. So because it is meters per second, it is the same as saying Lt power negative 1, Lt power negative 1, based from the units. So for this case, we shall have dimensions of V, they are going to be the same as dimensions of V, then we can take the square outside, whereby our V, since it is meters per second, it will be L, then T power negative 1. Now for this case, once you introduce in the dimensions, the square brackets must go away. Once you bring in dimensions, the square brackets must go away. So we have our square here. Now for this case, we shall come up with L power 2, then T power negative what? Power negative 2. These are dimensions of our left hand side. And for this case, it is V squared. Then we come on the right hand side, where we have Young's modulus divided by the density of the medium. So for this case, we have our right hand side. Right hand side is going to equal to dimensions of E divided by dimensions of what? Of density. But density, what are the signs for density? We are having kilograms per meter cubed. And kilogram, this is mass. Whereby mass, we use capital what? We use capital M. Then it is kilogram per meter cubed. So we shall be having capital M, then L power negative 3 for density. So we can begin by splitting it here. We look at one by one. So we shall have our E. Let us begin by looking at E only, whereby E, dimensions of E is going to equal to dimensions of F, L divided by A, E, because that is our Young's modulus. Now, force is given by mass times acceleration, whereby dimensions of mass here is supposed to be capital M. Acceleration, the units are supposed to be meters per second squared, whereby meters it is L. And this is the same as acceleration, it is meters per second squared, whereby meters we lose L. Then because it is per second squared, it will become T power negative what? Power negative 2. So for this case here, our force is going to be, once I bring in dimensions, our force is going to be mass, which is M, then acceleration, it is meters per second squared, which will be L, then T power negative 2. Force is mass times acceleration, Mass, it is m, that is its dimension because it is mass. Then acceleration, it is meters per second squared. Meters, it is capital L. Then t per second squared, which is going to be t power negative what? T power negative 2. Now for this case here, this L here is the original length times our L, then divided by area is given by maybe length times width, which will give us L times L. Then extension is supposed to be it is a distance, which is supposed to be also L. So for this case, this one can cancel out with this one here, and we shall finally come up with dimensions of E. Dimensions of E, they are going to equal to, this is L squared. When L goes up here, we shall have M L power negative 1, then T power negative 1. Those are dimensions of what? Dimensions of E. Then we come on dimensions of density, because it is E divided by law. So dimensions of density, density is given by mass divided by volume, whereby mass here is going to be capital M, and then our volume is given by psi times psi, which will be L cubed. So we shall come up with our law as M L power negative 3. Those are dimensions of what? Dimensions of law. Now we come and find dimensions of E divided by law. Dimensions of A is M L power negative 1 T power negative 2, then divided by dimensions of law, which is M, capital M. Don't change here, because capital M is standing for dimensions for what? For mass. If you use smaller m, it becomes something different, and it has to be cancelled out. Then we have L power negative 3 here. If you apply indices here, we shall come up with L power 2, then T power negative what? Power negative 2. So if you come and compare our left-hand side, it is L squared, T power negative 2, and our right-hand side, it is L squared, T power negative what? Then you come and say, since dimensions of the left-hand side are equal to the dimensions of the right-hand side. So for this case here, our formula or our equation, the equation V squared is equaling to E divided by law is the dimensional consistency, since the left-hand side is equal to the right-hand side. Dimension is here. Now we are using the square bracket. Don't forget here, square bracket C, they are always showing dimensions. Once you introduce the dimensions, the square brackets must go away. As you observe from this working here, dimensions of law is equal to mass divided by volume. Because I'm still looking at the quantities here, once I bring in dimensions here, I happen to come and use these other brackets, the curved brackets, because these ones are only used to show dimensions, or to show dimensions of a given physical quantity. Once the quantity has been introduced, once dimensions have been introduced here, you must remove the square brackets. That is a common mistake learners normally do. Once introducing the dimensions, the square brackets must go away. That is part B, Roman numeral 2. Now, when we come to part C, Roman numeral 1, they are saying state the law of conservation of linear momentum. State the law of conservation of linear momentum. When it comes to laws, you cannot change anything. We mark what is stated, what is given. We don't change anything because laws cannot be changed. since you're not the person who came up with that with that law. Now, the law of conservation of linear momentum, that is part C, number 1. This law states that for a system of colliding bodies, total momentum is always conserved or remains constant unless acted upon by an external force. So the law of conservation of momentum, the law of conservation of momentum, of linear momentum, states that that if a system of colliding bodies, total momentum is a constant, unless acted upon by an external force, unless acted upon by an external force. The law of conservation of linear momentum says that for a system of colliding bodies, total momentum is a constant unless acted upon by an external force. Or you can say the sum for a system of colliding bodies, total momentum before collision is equal to total momentum after collision unless acted upon by an external force. Now, this must be captured as you're stating the what? As you're stating the principle or the law, unless acted upon by an external force. So it only applies if there is no external force acting on these colliding bodies. So if you're having some external force which comes and plays a part as these bodies are colliding, what happens? Momentum will always not be conserved. That is the principle of conservation of linear momentum. Now, number 2 of part C, they are saying a bullet of mass is fired at a speed u into a bullet of mass m is fired at a speed u into a wooden block of mass m, suspended freely using a light string of length L. The bullet gets embedded into the block, and the combined mass swings through a height h before coming to rest. They want us to show that the angle of inclination of the string to the vertical is given by theta is equal to arc cos of 1 minus v squared divided by 2gl, whereby L is the length of the what? Of the string, and the v squared, I think it is the velocity of the bullet and the wooden block after colliding. Now, arc cos. So for this case, this is part C. Part C, Roman numeral 2. They want us to show that the angle of inclination is given by arc cos of 1 minus v squared divided by 2g what? 2gl. Now, for this case, we shall begin by drawing an illustration showing the motion of these two bodies on contact and after moving and covering a given distance. So for this case, we begin by doing a sketch. We have our initially our block was here. Then on colliding with this block here, the block will raise. But as this block is raising upwards, what happens? What happens is that it will be losing kinetic energy, but it will be gaining potential energy. Now, the length from here up to here is going to be the length of the what? Of our string, which will still be the same as here. Now, for this case, our angle of inclination with the vertical theta. Now, from here, we shall have this height here. I'm going to call it h. Now, the bullet comes from this side, and this bullet is having a velocity u meters. So they come and they collide with this wooden block and they move together. Now, on moving together, they will be going this side here. But as they go this side here, what happens? The block and the bullet, they will be losing kinetic energy and gaining potential energy, because the velocity will be reducing, whereas the height above the ground is going to be increasing. Now, for this case, we shall come and first get the length. Now, this side here. If you look at this point here, we shall form a triangle here, whereby the distance from here to this point here is going to be given by, if you apply the trigonometric ratios here, we shall have cos of theta, which is the angle of inclination, is always given by the adjacent divided by hypotenuse. So my adjacent is going to be given by L cos what? L cos theta. Now, if you observe from here up to here, it is L. But from here, from this point here, up to the point of suspension, it is the adjacent. So that means my H is going to be given by L minus L cos what? Cos theta. That's going to be the height. Now, if we come and applying the principle of conservation of mechanical energy. So remember that as the system is moving upwards, it will be losing kinetic energy but gaining potential energy. So for this case, our initial Ke, which will be given by a half mv squared, whereby this v here is standing in for the common velocity of the block and the bullet, is going to equal to mgl. So for this case, m is going to cancel out. We shall come up with v squared is going to equal to 2gl. That will be our v. Now, but remember that actually this was supposed to be h, not g. This is h, 2gh. But remember that our h is given by L minus L cos theta. So you have v squared is going to equal to 2g L into 1 minus cos theta. So dividing both sides by 2gl, divided by 2 what? 2gl. Our v squared divided by 2gl is going to equal to 1 minus cos what? Cos theta. Now, this cos theta is going to go the other side. This is going to come this side here. So we shall come up with cos theta is going to go to 1 minus v squared divided by 2gl. So for this case, we shall have, if you make theta the subject by taking aka cos, our theta is going to equal to aka cos of 1 minus v squared divided by 2gl. And I think this is the expression they want us to come up with. That is the expression. Okay. Let me try to increase on the size as people are saying. I think people have been complaining about the size. This one is better now. That size is better. So I think people have been complaining about the size. This size is better. So that is part C. That is part C. Yeah, we have been looking at this part here. A bullet of mass is fired at a speed u into a wooden block of mass m, suspended freely using a light string of length l. The bullet gets embedded into the block, and the combined mass swings through a height h before coming to rest. Show that the angle of inclination of the string to the vertical is given by that expression. Theta is equal to arc cos of 1 minus v squared divided by 2ga divided by 2gl. And we have come up with our solution as you see it here. So we came up with an illustration here. Our bullet is coming with this velocity here, hits this block here that is tied here, and they start moving upwards to cover distance h above the initial position. So for this case here, we have this adjacent here. I can even call it A. Can call it this one A, which is this adjacent here. So we have this triangle here. If you apply the trigonometric ratios, and specifically we have theta, cos theta, is given by adjacent divided by hypotenuse. Our hypotenuse is L. So we come up with our A as L cos theta. So from here up to here, we have it as L cos theta, following this triangle here. So our H is going to be from here up to here, minus from here up to here, to give us L minus L cos theta. That is going to be our expression. Now, if we come and apply the principle of conservation of mechanical energy here, we have a half mv squared, whereby this v is the velocity, common velocity of the ball and the bullet. Then we shall come up with our v squared is going to equal to 2gh. But our h is equal to L into 1 minus cos theta divided by 2gl divided by 2gl. We are coming up with cos theta as 1 minus v squared divided by 2gl. Then we come and take arc cos on both sides to come up with that expression. Okay. Let us proceed to part C. Let us proceed to part C. Now, part C, it is part D. Part D, they are saying a ball is projected horizontally from the edge of a pool table at a speed of 80 meters per second and strikes the ground a distance of 2.4 meters from the edge of the table. They want us to come up with the height of the table, velocity with which it hits the ground. So for this case, we have our ball is projected horizontally at that velocity, and it covers a distance of 2.4 meters from the edge. So we shall come and have an illustration of this. We shall come and have an illustration of this. So part D, we have our table here, and this ball has been projected horizontally, but afterwards it produces a trajectory. So I have it here, whereby the horizontal distance covered here is 2.4 meters. Then here, initially it was given an horizontal velocity of 8 meters per second. 8 meters per second. Meters per second. They want us to come up with the height of the table, velocity with which it hits the ground. Now, for this case, we shall come and consider horizontal motion. Horizontal motion. Remember that when a body is moving horizontally, it's not affected by gravity. So for this case, my S.6 has been given as 2.4 meters. From the second equation of motion, we have S is equal to ut plus a half gt squared. But for this case, our g is 0 meters per second squared because it is moving horizontally here. We're looking at horizontal motion. We shall have our S.6 is going to equal to ut, whereby our u is going to be 8 meters per second. So 2.4 is going to equal to 8 times t. Divide by 8. Divide by 8. Our t is going to equal to 0.3 seconds. That is going to be our time taken for this ball here to move from the point of projection to the point where it hits the ground. Then, but they want us to come up with height. Now, when we come on the vertical motion, we shall have our Sy is going to equal to uy t plus a half gt squared. But remember, initially, this ball was given an horizontal velocity. What does it mean? That initially, it doesn't have any component in the vertical. So our uy is going to equal to 0 meters per second since it was given an initial horizontal velocity. So our sy is going to be a half gt squared, whereby our sy, if we come and substitute, it's 1/2 times 9.81 times 0.3 squared. We shall have our SY. Now here we get our calculator and multiply to find the what? Find the final answer. 9.81 divided by 2 times 0.3 times 0.3. I am coming up with our SY as 0.44145 meters. And for this case, it is going to be our height, our h here. So our h is 0.44145. That is going to be our vertical height. Now, part two. People are telling me that my screen is not seen. Are you now able to see my screen? I'm sorry about that. Are you now able to see my screen? Oh, that's good. I'm sorry, I think I tapped somewhere. Yeah, okay. Okay, that's good. Okay, someone has said that we should repeat the solution. Okay, now this is our sketch. I began by looking at the horizontal motion, which was horizontal displacement was given as 2.4. So our S.6 is given as 2.4. But for horizontal motion, our g is 0, because a body moving horizontally is not affected by gravity. So we have our S.6 is going to equal to ut, whereby our u was given as 8 meters per second. So when you come and put in this equation here, 2.4 is going to equal to 80t. Divide by 8 on both sides. We are coming up with our time taken for this ball here to land on the ground as 0.3 seconds. Then vertical motion, when you come on vertical motion, now remember that this ball here was projected horizontal at first. So what does it mean? Initially, horizontally, it does not have a component in the y. The vertical component of velocity initially is going to be 0. So we shall come up with our SY is going to equal to 1/2 gt squared when uy is 0. We come and substitute in to come up with the height of the pool table. And for this case, we are getting the height as 0.44145 meters. That is our h from our diagram here. So that is Roman numeral 1. Roman numeral 2, I want us to look at now at Roman numeral 2, which is saying, Roman numeral 2 is saying velocity with which it hits the ground. Now, as this ball is going to be hitting the ground, it will hit the ground with a velocity in the horizontal, a velocity in the vertical, and these two components here, they will end up giving us the resultant velocity. So we shall come and first get the Vx, whereby Vx is going to be the velocity in the horizontal at that instant as it is the ground. But remember that the horizontal motion velocity remains the same. It doesn't change. So for this case here, we shall have our VXC is going to be the same as UX. And our VXC is going to be the same as 8 meters per second. Then we come and get Vy, whereby Vy is given by Uy then plus Gt. But remember that Uy is 0 since initially this ball was thrown horizontally. So we shall have Vy is going to equal to Gt. But of course, G is given as 9.81 from our cover page. Time is 0.3. We can get our Vy. If you use a calculator to find the Vy, our Vy is we are coming up with our Vy as 2.943 meters per second. That will be the Y component. Now our V is given by, that is resultant velocity. Resultant velocity is going to equal to Vxc squared, then plus Vy squared. So our V is going to equal to square root of Vx is 8 squared, then Vy is 2.943 squared. We use our calculator to find the answer. So I'm getting our V as square root of 72.61249. So we have our V as, when you take square root here, we shall have square root of that answer, 72.66124.9. We are getting our V as 8.52 meters per second. This will be the velocity with which this ball is going to hit the ground. It's going to hit the ground. That is Roman numeral 2. So that is the working for that question. That is the working for that question. I think we can move on to question 2. Then from question 2, we shall also look at some questions from the section B. So that was part D of question 1. Then in question 2, they're asking us to define the following terms. The first one is parking orbit. The second one is angular velocity. The third one is centripetal force. You see, all these terms are coming from circular motion. All these terms are coming from circular motion. So let us begin by defining the first term. The first term is parking orbit. Now, parking orbit is brought about by what we call geostationary satellites. Those that they say that move at the same speed as the Earth. So parking orbit is the space in the path of a satellite that makes it to appear stationary relative to an observer on the Earth's surface. So the first term is parking orbit. Parking orbit is a space in the path of a satellite that he make it appear stationary relative an observer on the Earth's surface. That is parking orbit. That is term 1. Now term 2, this is number 2, part A. Term 2, they're asking us to define angular velocity. So angular velocity is the rate of change of angular displacement. Is the rate of change of angular displacement. That is angular velocity. And the last term, they want us to define centripetal what? Centripetal force. Centripetal force, whereby our centripetal force, this is a force that is acting on an object moving in straight path, directing towards the center of the what? Is a force acting on an object moving in a circular path, and is directed towards the center, of the circle. So centripetal force is a force acting on an object moving in a circular path, and this force is always directed towards the center of the circle. All bodies moving in circular motion, or maybe described as circular motion, they experience this force. This is the force that is responsible for keeping them in that kind of what? In that kind of motion. That is centripetal force. So then let us look at the second part, that is part B. Part B, they want us to state Kepler's laws of planetary motion. So we are looking at let us look at the first law. Part B, they want us to state Kepler's laws of planetary motion. Looking at the first law states that planets describe elliptical orbits. With the sun at one focus. Planets describe elliptical orbits with the sun at one focus. So the first law, Kepler's laws, planets describe elliptical orbits with the sun at one focus. That is the first law. The second law, the imaginary line joining the sun and the planet sweeps out equal areas in equal time interval. That is the second law. The third law, the squares of the periods of revolution of a planet about the sun is directly proportional to the tube of the mean distance from the sun. To the planet. That is the third law. The squares of the periods of revolution of a planet about the sun is directly proportional to the tube of the mean distance from the sun to the planet. That is our third law, Kepler's third law of planetary motion. Supposed to be at one focus. Planets describe elliptic orbits with the sun at one what? At one focus. Planets describe elliptic orbits with the sun at one orbit, at one focus. Then the second law, the imaginary line during the sun and the planet sweeps out equal areas in equal time intervals. The third one, and the common one, the squares of the periods of revolution of a planet about the sun is actually proportional to the tube of the mean distance of the sun, from the sun to the planet. Those are the three laws of planetary motion. Now, part 2, number 2 of part B, a satellite moves in a circular orbit of radius r about a planet of mass m. With the period t. Show that r cubed is equal to gmt squared divided by 4 pi. In simple terms here, they want us to prove the third law according to Kepler. The third law according to Kepler. Now for this part here, we shall begin by, remember, Newton's gravitational law states that F is equal to G, mass of one body times mass of the body that is moving around divided by r squared. And it is this force here that provides the necessary centripetal force that gives this celestial body or this body here into motion. So this is the same as mass of the planet times omega squared angular velocity times r. So we shall come up with our g m, small m divided by r squared is the same as m omega squared times r. And for this case here, our m, small m is going to cancel out. So we have g m divided by r cubed is going to equal to omega squared. But our omega squared, our omega is the same as 2 pi divided by t. Then we come and substitute here. We shall come up with our g m. So we have our f is equal to g m divided by r. That is Newton's gravitational law. And it is this force here that is responsible for providing the necessary centripetal force to keep this body in motion. Gm m is equal to divided by r squared is equal to m times omega squared times r, whereby this r here is the radius of the orbit of the planet and that given satellite. Then small m is standing in for the mass of the satellite. Then capital M is standing in for the mass of the planet, and the G is the gravitational constant. Omega is the angular velocity. Now this m and this one they will cancel out, and I will come up with m divided by r cubed is equal to omega what? Omega squared. But our omega is the same as 2 pi divided by t. So we have our dm divided by r cubed is going to equal to 2 pi divided by t, but now squared. And for this case, we shall have our gm divided by r cubed is going to equal to 4 pi squared divided by t squared. Can cross multiply here. We shall come up with our r cubed is going to equal to gm t squared divided by 4 pi squared. Now for this case, as you see, this part here, that part there is a constant. So I can simply say that my r cubed is directly proportional to t squared, whereby the constant may be k is going to be given by k gm divided by 4 pi squared. And this is Kepler's third law of planetary motion. R cubed, the square of the periods of revolution is directly proportion the cube of the mean distance between the sun and the planet. In simple terms, part B was going for derivation of Kepler's third law. That is part what? That is part B, Roman numeral what? 2. So our facilitation is ending at 6. Is probably going to end at 6. These questions have been shared. Now on this part here, diagrams are not required because they don't carry any mark. Diagrams are not required. But about the questions are going to be shared to you. We shall get the questions, and I promised you to share with you the solution guides for all these questions here. Okay. So that is it. People are asking about diagrams. For this case, the diagram is not required. It won't take any mark, but you can draw it maybe for better interpretation. You can draw it for better interpretation. So part C, they are saying, explain the effect of frictional resistance to the motion of the state light. Explain the effect of frictional resistance to the motion of the state light. Now, as these states are moving in space, they experience some opposition. And this opposition is due to air resistance as they are moving. So because of this here, they have to do work. They have to do work against friction. And by doing work against friction, what happens? There will be a reduction in the total energy possessed by this state light here. And when there is a reduction in KE, what happens? The state light will go into a lower orbit. And by going into a lower orbit, what does it mean? The kinetic energy of this body here is going to increase. And the state light is going to start moving at a very high velocity. And by moving at high velocity, this is going to end up leading to an increase in the temperature of the state light. And eventually, this state light here is going to end up burning up in the Earth's atmosphere. So now, as you know that the Earth has an atmosphere, and this atmosphere is mainly made up of gases. So what happens is that as it is moving in space, it experiences some opposition due to air, and when it experiences some opposition, work has to be done to overcome this opposition. And when work is done, the state light is going to lose energy. All its total energy is going to decrease, but there will be an increase in kinetic energy because KE is inversely proportional to the distance of the satellite from the planet. So the increase in KE implies that the satellite is moving at higher velocity. And by moving at higher velocity, there will be an increase in the temperatures of the satellite here. And the increase in the temperature may end up leading to burning up of the satellite in the space. The formula, our KE is given by Gm divided by 2 pi r. It's given by Gm times small m divided by 2r, whereby r here is going to be the distance of the satellite from the center of the Earth or from the center of the planet. Now let us look at we can give the explanation. We can give the explanation for effect of air resistance on the motion of the satellite. Now for this case, a moving satellite in the Earth's atmosphere experiences friction due to the gases in atmosphere. So a moving satellite in the Earth's atmosphere experiences friction due to the gases that are present. So work has to be done to overcome this resistance. Work has to be done to overcome this resistance. And the state light drops into a lower orbit due to decrease in total energy, but it experiences an increase in Ke, since Ke is equal to Bm m divided by 2 pi r. So what happens is this leads to an increase in velocity and increase in temperature of the state light. So after some time, and eventually the state light burns out into space. So as the moving state is moving, experiences some air resistance due to the presence of the gases in the atmosphere, and work has to be done to overcome this resistance. And now on overcoming resistance, the state light loses the energy, total energy reduces, thereby dropping into a lower orbit. And by dropping into a lower orbit, the Ke is going to increase, since Ke is inversely proportional to the distance of the satellite from the center of a given planet. Now, the increase in Ke is going to lead to an increase in the velocity of the what? In the velocity of the state light. And this will eventually lead to an increase in temperature, and then the state light may end up burning up in the Earth's atmosphere. So whenever there is resistance leads to increase in Ke, because it has to drop into a lower orbit in such a case. That is the simple explanation about the effect of air resistance on the motion of the state light. So that is the part. Then part D, the period of oscillation of a conical pendulum is 2.0 seconds. If the string makes an angle of 60 degrees Celsius, 60 degrees to the vertical at the point of suspension, they want us to come up with the vertical height of the point of suspension above the circle, length of the string, velocity of the mass attached to the string. So let us look at this question. We have a conical pendulum and is moving this way with circular motion at an angle of 60 degrees, and the period of revolution is given as 2 seconds. So for this case here, we have our conical pendulum. So this will be the radius of the circle. Now for this case, we shall be having tension T. Then here we shall be having weight mg of the ball. Then here we shall be having the centripetal force m omega squared r. Then tension, if you resolve it here at this angle of 60, it will give us two components. One is going to be T cos T sine what? Sine 60. Then here we shall have T cos of 60. Our periodic time is given as 2 seconds. This is the tension. So now for this case here, concerning the equilibrium state, we shall have T cos theta cos 60 is equal to mg. That is our first equation. Then we have T sine 60 is equal to m omega squared r. This is our second equation on this conical pendulum. Now, if you say equation 2 divided by equation what? Equation 1. So we shall have this one divided by this. It will give us this and this. We shall come up with tan 60. This divided by this, it will give us omega squared r divided by g, whereby our r is going to equal to g tan of 60. Then all of it divided by omega squared. But remember that our omega is given by 2 pi divided by t. So our omega is going to equal to our t has been given as 2, which will be 2 pi divided by 2, which will give us pi. These are going to be that z per second. So we can come and substitute in here to get our r. Our r is going to equal to 9.81 tan of 60 divided by pi squared. Pi squared. Then we can substitute in using our calculators. 9.81 tan of 60, then divided by pi squared. I am getting r as 1.72 22 meters. That's the radius of the circle. Now, second part, they're asking us to find the length. Actually, the first part, they're asking us to find the vertical height of the point of suspension above what? Above the circle. They want us to come up with this h. Now, h by using the cos. Let us use the tan. Tan 60 is going to equal to r, which is this part here, divided by h. So our h is going to be r divided by tan 60. R we have got 1.722 divided by tan 60. And get our h. Our h is going to be given by 1.722 divided by tan of 60. I am coming up with h as 0.994 meters. That is our height. Then the second part, they want us to come up with the length of the string. Length of the string. Length of the string is going to come and do it here just by simply using the trigonometric ratios. If we come and use the trigonometric ratios here, they want us to find the length of the string here. That length, I'll come and I can use a sign whereby I'll have sine 60 is going to equal to opposite, which is r divided by l. So my l is going to equal to r divided by sine of 60. R 1.722 divided by our sine 60. We shall be able to come up with our length as 1.722 divided by sine 60. I'm getting our L as 1.988 meters. That is our R. That is our L, length of the string that was used to produce this conical pendulum. So about the decimal places here, let us try to avoid the overrounding of our values. You can always give your answer at least to the smaller places. Even when you use the pi as 3.144, I think it is okay. You can use that pi. You can use the pi, but you can also use the one for the calculator, and you get the answer. I'm sure to around 2 to 3 decimal places, you shall be having the same answer. So that is questioning. Then they want us to come up with the velocity of the mass attached to the string. Velocity of the mass attached to the string. Remember that our velocity V is given by omega what? Omega r, eh? But our omega is pi times 1.722. Then you can come up with our answer, which is 7 times our pi, which is giving us 5.4041 meters per second. That will be the velocity of the what? Of the attached mass. V is equal to omega r. So that is question 1 and question 2 of mechanics. I wanted also to look at maybe some item in it may be in heat. I want us to look at some item in heat. And let us discuss item 7. Let's discuss item 7. So heat, if you look at this paper here, we are having the calorimetry taking on question 5 and some part of thermometry on part D. Then part number 6, we are having the part of gas laws and thermodynamics, reversible process, adiabatic process. It has part of gas laws and the vapors. That is the question 6. Then in question 7, we are having heat transfer. We are having that is radiation. We are having heat transfer mainly on this question here. So I want us to look at one item. Because of time, I'm seeing time is not on our side. Maybe we also discuss one item in section B. I'll be sharing with you solutions to all these questions here on our different platforms. Maybe based on these items here, I can have your opinion about which item can we look at for the interest of time. Let us just decide which item can we look at here in heat. So let me allow majority to go with the majority. Which item should we look at? Suggestions are allowed before I can take on. I'm seeing people are saying questions will be shared via our platforms. I'm seeing most people are saying 7. Are saying 7. And for the interest of time, let us discuss item 7. Let's discuss question 7. Now, question 7, they are saying define the following terms: coefficient of thermoconductivity, describe the detection of infrared radiations using the ether thermoscope. Part 2. Let us begin with the definition. Let's begin with the definition. This is number 7. Now, number 7, the first part, they want us to give the definition of thermoconductivity. They want us to give the definition of thermoconductivity. Now, from our formula, our Q, rate of heat transfer, Q over T, that is rate of heat transfer, is given by K, A, change in temperature, then divide by L. If you make this K the subject, our K is going to equal to Q over T, all of it divided by A delta Q divided by L. Now, Q over T, that is the rate of heat transfer. And our A is always cross-sectional area. Delta theta is change in temperature. Then L is the thickness of the material. Now, which is the same as temperature gradient. Now, the definition of coefficient of thermoconductivity is defined as this is the rate of heat transfer per unit cross-sectional area per unit temperature gradient. So coefficient of thermoconductivity based on that formula here is the rate of heat transfer per unit cross-sectional area per unit cross-sectional area per unit temperature temperature gradient per unit temperature. Now, students normally make a mistake and say surface area. It's supposed to be per unit cross-sectional area. Is the rate of heat transfer per unit cross-sectional area per unit temperature gradient. That is a simple definition of thermoconductivity or coefficient of thermoconductivity. Oh, here I began by giving you this formula here to help you understand the definition of coefficient of thermoconductivity. So our rate of heat transfer in the material is given by coefficient of thermoconductivity times cross-sectional area times temperature change divided by the thickness of the material. If you make the subject here, we have our K is equal to 2 divided by T divided by cross-sectional area divided by temperature gradient. Then from this formula here, we can come up with a definition for coefficient of thermoconductivity as rate of heat transfer, which is this one here up, then per unit cross-sectional area because it is divided by area, cross-sectional area, then per unit temperature gradient because this divided by this one here, it gives us temperature gradient. I gave the first formula here to help us understand, to come up with a simpler way of coming up with a definition for thermoconductivity or coefficient of thermoconductivity. I think now it is clear. Now, part B, they want us to describe detection of infrareds using ether thermoscope. Remember, among the properties of infrared is here, infrared cause change in temperature. And because I'm using ether thermoscope here, it's always composed of liquid what? Liquid ether. Liquid ether has the ability to expand after absorbing what? After absorbing the heat. Now, for this case here, that is part B number 1. Part B number 1 shall begin with a diagram. Here we have our liquid ether enclosed in the tube which has uniform area. Now this part here is shining. This part here is blackened. Then inside here we shall have liquid ether. Inside here we have liquid ether, and this is a transparent. This is a transparent tube. So now for this case, we shall be having our radiations falling onto this transparent glass. Now what happens is liquid ether is trapped into a tube, transparent glass. This is liquid ether. This part here is blackened. Among the properties of black materials, they are good absorbers of radiations. So what happens is infrared radiations are made incident onto the tube containing liquid ether. Now, after some time, it is observed that the level of liquid ether in the shining part is going to be higher than the level of the liquid ether in the blackened what? Blackened side here. Now on the dark side here, being dark, it absorbs radiations very fast, and the ether is going to expand, pushing it to go in the other transparent, shining what? Transparent side. And this confirms the detection of infrared, that is using the ether thermoscope. It is a simple experiment. Then party Roman numeral 2, they are saying a copper of diameter 20 millimeters is cooled to temperature of 500 kelvins and then placed in an enclosure maintained at 300 kelvins. Assuming that all heat exchange is by radiation, they want us to calculate the initial rate of loss of temperature of the sphere assumed as a black body. Specific capacity of the copper is given as 400 joules per kilogram per Kelvin. So let us go through this question here. They are saying we have our copper which has a diameter of 20 millimeters, is equal to the temperature of this one. Now for this case, we shall be having heat exchange by radiation. So we have our copper. The radius is 20. Is it the radius or diameter? Diameter is 20. Diameter is 20. Diameter is 20 millimeters. The diameter is that. So our R is going to be 10 millimeters. So now our initial temperature of the copper is 500 kelvins. Then our new temperature is of the surrounding is 300 kelvins. Now our C for the copper material is 400 joules per kilogram per Kelvin. That is specific capacity of the copper. That is the specific capacity of the copper. What else has been given the question? I think that is all. So initial 500, then the surrounding is 300. They want us to come up with the rate at which the temperature is going to be dropping. Now, because it is placed in an enclosure here, this copper was at 500 kelvins. It is placed in an enclosure which is at 300 kelvins. So for this case here, we shall be having heat loss, whereby heat loss using Stephanie's laws here, we shall say P net is equal to surface area times sigma into T naught, maybe T1 power 4 minus T2 power what? Power 4. This is going to be lost by the what? By the copper, because the copper is at higher temperature, whereby S is the surface area, and because it is a sphere, surface area of a sphere is given by 4 pi r squared. 4 pi r squared. So you can get the surface area, which will be 4 pi into 10 divided by 1000 to take it to meters, which will give us 4 pi times 0.01 then squared to give us the surface area. So we can use our calculators and get the surface area, which is 4 pi times 0.01, but it is squared. I am coming up with our surface area as 0.00126 meters squared. Now we can get P net, whereby this P net here is going to be the power that will be lost by the what? That will be lost by the copper sphere. So our P net is going to equal to S is the surface area, which is 0.00126. Then the sigma, that is Stephanie's constant, which is 5.67, 10 power negative 8, into 500 power 4 minus 400 power 4, to get how much heat is going to be lost per second by the copper sphere. So we have 500 power 4, then minus 300 power 4 times 5.67 times 10 power negative 8 times our surface area, I am getting our P net as 3.887. These are going to be joules per second. Now, this is the amount of heat that will be lost by the what? By the copper sphere per second. But remember that our copper sphere, heat lost by copper sphere can still be given by mass times C times change in temperature. So whereby our mass is given by volume times density. But volume of a sphere is equal to 4 over 3 pi r cubed, which will be 4 over 3 pi times our radius, which is 0.001 cubed, to come up with our volume. So our volume, 4 divided by 3 times pi times 0.01 power 3 4 divided by 3 times pi times 0.01 power 3. I am coming up with the volume as 4.19 times 10 power negative 6 meters cubed. That is the volume. Now the density of the copper sphere was given on the first part. The density is given as the density of copper 8.39 times 10 power 3. That is the density of the copper sphere. 8.39 our density, 8.39 times 10 power what? Power 3 kilograms per meter cubed. So we can come and get the mass of this copper sphere. Our mass is going to equal to 4.16 times 19 times 10 power negative 9 times 8.39 times 10 power 3 to give us the mass. So the mass I'm getting 0.035 kilograms. That is the mass of the copper sphere. So I come and equate these two, that pin net, what is lost here is going to be equivalent to what is absorbed. 3.887 is going to equal to 0.035 times 400 times delta theta. Now, delta theta for this case is standing in for the rate at which heat is the rate at which the temperature is going to be dropping. So we have 0.3 times 400. So I'm having 3.887 is equal to 14.06 delta theta divided by 14.06 divided by 14.06. Our delta theta is going to equal to 3.887 divided by 14.06. I'm coming up with 0.276. These are going to be kelvins per second. So the rate at which the temperature is going to be dropping is going to be 0.276 kelvins per second. That is going to be the rate at which the temperature of our copper block is going to be dropping down. Is going to be dropping down. Okay. So that is the solution for this question. That is part 2 of Roman numeral of part B. Then part C, if a copper kettle has a base of thickness 2.0 millimeters and an area of 3.0 times 10 power negative 2 meters squared, estimate the steady difference in temperature between the inner and the outer surface of the base, which must be maintained to enable enough heat to pass through so that the temperature of 1 kilogram mass of water rises at a rate of 0.25 kelvins per second. Assume that there are no heat losses. After reaching the temperature of 373 kelvins, the water is allowed to boil under the same conditions for 120 seconds. And the mass of water remaining in the kettle is 0.948. That is part C. So that is part C. I want us to go through part C, and I think we may end here for the interest of time. So part C, we have a copper kettle and has a base of thickness 2.0 millimeters and an area of 3.0 times 10 power negative 2 meters squared. They want us to estimate the steady difference in temperature between inner and outer surface. Now, this is part C. Our thickness is 2 So here we shall be having our rate of heat transfer Q over T is given by Ka delta theta divided by L. And because this heat is going to be transferred to the water, it will be mc delta theta divided by time. Now, this is going to give us the rate at which the temperature is going to be what? Increasing down for water. Now, what they're asking us to get here, they want us to estimate the difference now, whereby our K was given as from the question. K was given. It is a copper kettle. So we can go back on our cover page and look at the thermoconductivity of copper, which is 3.8 times 10 power 2. So our 3.0, our K is already given as 3.8 times 10 power 2. And our area was given as, from the question, the area is given as, area has been given as 3.0 10 power negative 2. Area 3 times 10 power negative 2 meters squared. And our thickness has been given as 2 millimeters. So the thickness is 2 millimeters, which is the same as 2 times 10 power negative 3 meters. The mass of water initially was 1 kilogram. And seawater, specific mass of water is 4,200 joules per kilogram per Kelvin. Now we can substitute in here, and our delta theta divided by T has been given as, if you go back on the question, it has been given as 0.25 kelvins per second. That is the rate at which the temperature of the liquid is going to be increasing. So our delta theta is given by 0.25 kelvins per second. And they want us to come up with delta theta, whereby delta theta for this case here, for this one here, so let me close in plain. Delta theta for this case here, that is the difference in the inner, on the outer and the inner surface of the kettle. So we come and substitute in here. Our K is 3.8 10 power what? 2 times 3 times 10 power negative 2 delta theta divided by our L, which is 2 times 10 power negative 3, is going to equal to mass, which is 1 times 4200 times 0.25. So we shall have delta theta, the difference in temperature, 4200 times 0.25 times 2 times 10 power negative 3, then divided by 3.8 times 10 power 2 times 3 times 10 power negative what? Power negative 2, to come up with a difference in temperature between the inner and the outer surface. 4200 times 0.25 times 2 times 10 power negative 3. I'm coming up with 2.1. Then we shall have 3.8 times 3, which is giving me 11.4. So 2.1 divided by 11.4. I am coming up with our change in temperature between the inner surface and the outer surface as 0.184 kelvins. That is between the inner surface of the kettle and the outer surface. So that is our expression, that is our answer for the difference in temperature. That is going to be our working. When you substitute in here, in this equation here, K, you're starting for area, delta theta is not known, divided by the thickness, M is 1 kilogram, C is 4,200, and delta theta divided by T is given as 0.25. Make delta theta the subject here. We are coming up with the steady change or the steady difference in the temperatures of the outer and the inner surfaces as 0.184 kelvins. That's the difference between the outer and the inner surface of this kettle here. Now, Roman numeral 2, they want us to find the value of specific latent heat of vaporization. Now, for this part here, they are saying after reaching the temperature of 373, and that is the boiling point, the water is allowed to boil under the same conditions for 120 seconds, and the mass of water remaining in the kettle is 0.948 kilograms. So what does it mean? Some of it has evaporated. So here we consider that the rate of heat transfer is equivalent to the rate at which it is being supplied. So we have our time. Time has been given as 120 seconds. Now we have 2 divided by T is the same as M L what? LV, whereby the rate at which is going to be transferred is going to be equivalent to the rate at which the water is going to be evaporating. But our aim is going to be 1 minus 0.94, because that's what was remaining in the what? In the kettle, 948, to come up with the mass that evaporated. So our aim is going to equal to 1 minus 0.948, which is going to give us 0.052 kilograms. But now this mass here evaporated in 120 seconds. So we can come and find the mass that evaporates per second by saying 0.052 divided by time to come up with the mass that evaporates per second. Then our Q over T is the same as Ka delta theta divided by L. And this one is going to be the same as 3.8 power 2 times 10 power 2 times 3 times 10 power negative 2. Our delta theta, we had got it as 0.184 times 0.184. Then all of it over 2 times 10 power negative 3, because it was in millimeters. Then this one is equivalent to MLV. So you have 3.8 times 3, 0.184, divided by 2 times 10 power negative 3. I am having 1, which is going to go to our M is 0.052 divided by 120, then LV. M was 120 divided by 0.052. I am coming up with our LV as 2.42 times 10 power 6. These are going to be joules per watt per kilogram. This is going to be the specific latent heat of vaporization of water. That is going to be the value that we have come up with. And because of time, I would like to end here. Maybe we can have another. We shall be having another discussion with time. I'll be sharing the questions, and I'll be sharing the solutions of this paper. So, Teacher Stephen.
Yes, thank you so much, Teacher Moses, for the wonderful session. Dear members, we shall have time for another paper, but also Teacher Moses will be able to come back at one point to continue discuss for us. We shall let you know the exact dates when we shall have that session, but I want to thank Teacher Moses for this wonderful session, and please do not get tired whenever we call you on to support this country in this direction. Thank you so much, and we want to wish you a good evening. Thank you so much, dear teachers and all the children that have attended this session. We shall share the recording before today ends. Have a good day and a good... Yes, Teacher Moses.
Maybe before you close up, people have been asking where can they get the questions? How can they access these questions?
The questions are going to be shared on the different WhatsApp groups this evening, and also we shall share them on the Padlet platform, so they will be able to access them.
Okay.
Okay, thank you so much, and have a good evening, everyone.